Um, okay, so, well, welcome everybody to today's colloquium, which obviously is at an unusual time. So it's a real pleasure to have Mark Zhandry here. Mark is on the faculty at Princeton. He has a very distinguished career, starting work in classical cryptography, but increasingly dipping into the quantum aspects of the subject. And so I can't, think of anyone better to talk to us about post-quantum cryptography. So thanks, Mark. And
yeah, thank you for the introduction, and thanks to everyone for accommodating my schedule and having this meeting at an unusual time. So should I get started?
Yes, please.
Okay. All right. So I'll start with a whirlwind tour of the history of crypto. So crypto is a really ancient practice dating back about 4,000 years. So the first phase I'll call pre-modern crypto. And basically this was characterized this era was characterized by a tug of war between the code makers and code breakers. And it was this, continuous cycle of design a code, clever attack to break it, design a new code, etc. Something really important changed though in the 1900s. And there are really actually three things that really revolutionized crypto. One is technology, and specifically computers. The introduction of technology into cryptography helped in cryptanalysis efforts during World War II and beyond, and it also allowed the code makers to move beyond the pencil and paper type ciphers that could be done by hand that had characterized crypto for ages. And by using more complex codes, this made the cryptanalysis exponentially more difficult. The other big thing that changed in crypto was the introduction of formalism. So now we have precise definitions of what it means to be secure, and we have rigorous proofs of security. And as a result of this, today really hacks are not usually the result of crypto being broken, but they're instead the result of social engineering, bad practices, traffic analysis, things like that. The crypto is not the weak link. And the other big thing was the realization that cryptography wasn't just about encryption. And there's all sorts of things. There's public key cryptography, which allows for parties who've never met and don't have a shared secret key to be able to securely communicate. There's things like zero knowledge proofs, how to prove a theorem without actually revealing the proof, multi-party computation, how to have a bunch of mutually distrusting individuals compute a joint function on their inputs, and the list goes on and on. So this is modern crypto, which has characterized crypto for the last several decades. And what we're starting to enter now is the next phase of crypto, which is post-quantum crypto. This phase will be characterized by the emergence of quantum computers, which seem like they're coming, and quantum computers will really require us to visit all three of these main features of modern cryptography. So the enhanced computational power of a quantum computer will mean that codes are broken. We'll now need to reason about quantum computation in order to justify the security of our crypto systems. And on the other hand, maybe by running a quantum computer, there's that can be achieved that were never before possible. All right, so for this talk, I'll be giving a brief overview of the threat that quantum computers bring to cryptography. So mainly focusing on the first two things, and I'll just briefly mention the new applications at the very end. So the first thing is I need to clarify what I mean by we now have rigorous proofs of security. So, the most famous problem in computer science is this P versus NP problem, basically whether the ability to verify solutions efficiently mean you can compute the solutions from scratch. And the fact is that we don't know the answer to this question. But it turns out that if it were resolved in the positive, meaning if P were actually equal to NP, it turns out that most crypto would be impossible. So the entire field of cryptography is based on the widely believed but unproven assumption that at least P is not equal to NP, that there are problems that you can verify that, but you can nevertheless not find solutions from scratch. And right, so most crypto relies on P not equal to NP, and in fact, it will rely on even more specific computational assumptions, the hardness of specific instances, such as the hardness of factoring, discrete log, certain hard problems on lattices, like finding shortest vectors, inverting particular hash functions, and so forth. So all of crypto, or not all, but most of crypto is based on some assumption like this. And what this means is we have to really clarify what we mean by a crypto security proof. So here's what I'll call the fundamental formula of modern cryptography, which is that a crypto security proof has three components. So the first is some computational assumption, let's say the hardness of factoring, and then a precise security definition of what you're trying to achieve. So a formalization of what it means to be a secure encryption scheme or whatever. And then something called a reduction, which shows how to shows that solving P, to solve P, it suffices to break D. Or put another way, if you can attack the crypto system, then you are able to solve the underlying presumably hard computational problem. So if you're able to break the encryption scheme according to the security definition D, then you can transform that algorithm into an algorithm that factors integers or something like that. So the problem when we move to this third era of cryptography, where we are starting to consider quantum computers, is that the typical literature only considers the classical versions of all of these three ingredients. So when we move to a setting with quantum computers and we want to justify the security of our crypto system against an adversary who may have at their disposal a quantum computer, we need to first make sure that the assumption is actually secure against quantum computers. So we need a post-quantum assumption. This requires us asking which assumptions are still plausible once we have a quantum computer. We need a precise security definition for quantum attacks. And this raises the question of what kind of quantum attacks are possible. And then we need a reduction that transforms an attacker for our post-quantum definition into an attacker against our starting assumption. And in this reduction, we need to then reason about quantum computation, not just classical computation. So all three of these ingredients need to be revisited once we move to the quantum setting. So first, I'll just briefly talk. So in this talk, I'll talk about all three of these ingredients. I'll start just by briefly talking about cryptographic assumptions. So there are sort of three categories of cryptographic assumptions for our purposes. The first is going to be these ones on the left here, such as factoring and discrete log, that appear to be hard for classical computation, but due to Shor's algorithm, it turns out that these problems are actually easy on a quantum computer. So once we're moving to post-quantum cryptography, we can no longer base security off of these assumptions because they no longer hold. So that's the first category. The second category are concrete hash functions or block ciphers, things like that, that are not based on algebra. And these will be crucial in a post-quantum setting. They are not broken by quantum computers. But it turns out that these have limited applications. Many of the amazing applications that cryptographers have discovered over the last few decades cannot be achieved by this category. And so the final category are these algebraic type of assumptions, like solving multivariate equations, computing isogenies between elliptic curves, hard problems on lattices, that appear to be resistant to quantum computers and also are capable of achieving all of these amazing applications. And because of the ability to achieve these applications while resisting quantum attacks, most of the attention has been placed on these assumptions, and in particular, lattices have been sort of the main focus of post-quantum cryptography. I'll also just briefly mention that there's more than just Shor's algorithm. There are some partial attacks, such as Grover's algorithm and Kuperberg's algorithm, that apply to different subsets of these problems that weaken them but don't break them, and you can usually compensate for these attacks by increasing parameter sizes. So that's more or less all I wanted to say about cryptographic assumptions. I just wanted to mention a key takeaway from all this is that essentially all of the total quantum attacks, the ones that render the computational assumptions completely broken, essentially all of them are view the assumption as an instance of something called period finding, or the hidden subgroup problem over abelian groups. So Shor's algorithm for factoring a discrete log basically views, somehow shows that if you can find the period of a function, you can factor integers. And the way that this is done is you define this function f of a that just takes g to the a mod n. If you find the period of this function f, well then if you raise g to the period over 2, what you get is a square root of 1. And it turns out that computing square roots of 1 mod a composite allows you to factor. And discrete log you can also view as a period finding, sort of a multi-dimensional period finding, where your input is a 2-dimensional vector, and you define your function like this. And it turns out that the period of this function actually immediately tells you the discrete log, the value a, such that g to the a equals h. So all of the total quantum attacks view whatever assumption they're attacking as an instance of period finding. And the ones that resist quantum attacks, we don't know of any reduction to period finding over abelian groups. Okay, so that with that out of the way, the rest of the talk is really going to focus on the other two ingredients of a crypto security proof, which are definitions and reductions. And the point is going to be to demonstrate that just basing your crypto system on lattices, which presumably resist quantum attacks, just basing your crypto system on any post-quantum assumption, it's not enough, and you really need to be careful when you're trying to justify the security against quantum computers. All right, so I'll give several examples that will hopefully sort of illustrate sort of the key challenges faced in post-quantum cryptography. The first example is going to be something called pseudorandom generators. So a pseudorandom generator is a deterministic function g that takes as inputs n bits, outputs m bits for some m greater than n. So it expands its input. And yet what we want, and here I'll just review sort of the classical case. So for the moment, nothing quantum is going on. What we want is that this output looks random. Now, of course, it cannot be truly random because it has only n bits of entropy from the input, if assuming the input is random. And the output is m bits long for m greater than n. So it can't be truly random. But the hope is that it can't be distinguished from random by any efficient adversary. So we say that G is a secure pseudorandom generator if for all efficient classical adversaries, because we're in the classical setting for now, basically this condition in the green box just says that no classical algorithm can distinguish a truly random truly random output y from g of x for a random x. All right, and we denote efficient classical time algorithms by this, we call it probabilistic polynomial time. We allow the adversary to be randomized, and we denote this PPT. All right, and just a bit of terminology. The difference here for a particular algorithm, the difference between the probability that it outputs 1 when given a random output versus the output of the generator, we'll call this epsilon the advantage. Okay, so that's classical pseudo-randomness. And now here's a question that you may wonder. Suppose I have a pseudo-random generator with some stretch. Like, let's suppose it even just expands the input by a single bit. But for some reason, I want to generate more randomness. You know, maybe I still don't have quite enough randomness to suit my needs. Well, it turns out that you can expand the randomness, but just by repeated application of the generator. So I have my n-bit input. I expand it via the pseudorandom generator to get n+1 bits. And then I take n of those bits, which happens to be the domain of the pseudorandom generator again. So I feed it through the generator again and get n+1 bits. And then I add the 1 bit left over from before, and I get n+2 bits. And you know, you can keep doing this as many times as you like to generate as much pseudo-randomness as you want. And we have a classical theorem that says that this works. That if the pseudorandom generator is secure, even if it just provides you with 1 extra bit of pseudo-randomness, then repeated application will also be pseudo-random. So let's go through the proof of this. This is sort of like a classical standard proof technique. So the way we prove security in the quantum set, or sorry, in classical cryptography, is by contradiction. So we assume toward contradiction that we have that actually our new pseudorandom generator that expanded by 2 bits. We assume that it's insecure, which means that there is a PPT adversary A with some noticeable advantage in distinguishing random from pseudorandom for this new generator G2. And what we're going to try to do from this is arrive at a contradiction by showing how to transform this adversary A into an adversary for the underlying pseudorandom generator, which we assumed was secure. All right, so the way we're going to do this is by something called a hybrid argument. And this is the bread and butter of crypto security proofs. So I'm going to define an experiment or hybrid 0, which is just the case where I feed the adversary a pseudorandom output. So an actual output of G2 on a random input. And I'm just going to define P0 as the probability that the adversary outputs 1 in this case. I'll define a second hybrid, hybrid 2, which is the random case, where A is just given a uniformly random string, and I'm going to define P2 as the probability that the adversary outputs 1 in this case. And then finally, I'm going to define this intermediate hybrid, which is sort of interpolating between hybrid 0 and hybrid 2, where the way the adversary's input is derived is the first n+1 bits are the output of the pseudorandom generator on a truly random input, and then the final bit is uniformly random. Right, so I've sort of replaced the first PRG with random, but I haven't gone all the way to replacing the entire input to the adversary with random. Okay, so what does this hybrid allow us to do? Well, first, we know that by virtue of our adversary A being a distinguisher, an attacker against the pseudorandom generator G2, we know that P2 minus P0 have to be large. That is just by the assumption that the attacker is an actual attacker. P0 and P2 correspond to the exact things that our attacker is trying to distinguish. So we know P0 and P2 are far apart. We don't actually know anything about P1. We're given nothing about the adversary other than the fact that it is an adversary. And all that tells us is that P0 minus P2 are far. So we don't know anything about P1. But what we can do is we can sort of break into two cases. So one case is that P1 is somewhat far from P0. And the other case is that P1 is somewhat far from P2. By the triangle inequality, one of these two must hold, right? Because P0 and P2 are far apart, P1 can't be simultaneously close to both of them. So we know one of these are true. And in either case, we can use the fact that P1 is far from P0 or the fact that P1 is far from P2 to derive an adversary for the underlying generator. So in the left case, our adversary looks like this, and in the right case, our adversary looks like this. Maybe I won't explain this, but the intuition is we just, the difference between these adjacent hybrids was one application of the pseudorandom generator. And if we were able to distinguish the adjacent hybrids, we can sort of isolate the one difference and use that to break the underlying pseudorandom generator G. But so the key takeaway is that in either case, no matter what happens with hybrid one, in one of the two cases, we're able to get an advantage in attacking G. Okay, so that's the classical proof of this theorem. Now, what happens when we move to the quantum setting? What happens when we now want to introduce quantum computers into the mix? Well, so first, our starting assumption we need to update to the assumption that our original pseudorandom generator is secure against quantum computers. Right, so we can update our definition of what it means to be a secure pseudorandom generator. Basically, you just replace any instance of probabilistic or classical, you just replace it with quantum. Right, so instead of PPT, we have QPT, where Q stands for quantum. Right, so this is straightforward. And then it turns out that we can also lift our theorem from the classical setting to the quantum setting, saying that if G, our little 1-bit stretch pseudorandom generator, if it is post-quantum secure, so if it resists quantum attacks, then it also resists, then the generator G2, which expanded by 2 bits, also resists quantum attacks. And the proof is actually essentially identical. So here's the same exact slide as before, except that I've inserted Q's in the necessary place. So we prove by contradiction. So we suppose that G2 is insecure against a quantum attacker. So that means that there exists a quantum polynomial time algorithm A with a non-negligible advantage epsilon. And everything we do is the same, except that the only difference is B is running A as sort of is running our original attacker as a subroutine. And since this subroutine is quantum, now B has to be a quantum attack against G. But otherwise, the proof is literally the same. And the fact that the proof is the same is actually part of sort of a broader principle. And the point is that our proof of security for G2 actually didn't care how the adversary that we started from worked internally. All it cared about was that it broke the pseudorandomness of the generator, which just meant that it had a non-negligible advantage, that it had a noticeable advantage in distinguishing random from pseudorandom. But it actually didn't care at all about how A worked internally. So A could have been a classical computer, taking a random or pseudorandom Y and outputting a bit B. It could have been a quantum computer, or it could have been something even crazier. It could have, been using closed time-like curves, or even just magic. It didn't matter. Basically anything thing that happens inside the box is irrelevant for the proof. And this is something that is sometimes referred to as a black box proof. And this is pretty common in crypto. And it's actually, curiously, it's a consequence of our inability to reason about polynomial time computation, is that we have to prove security in this way, where we sort of take an attacker, treat them as a black box because we don't know how to actually reason about polynomial time computation, and just sort of use the input-output behavior of the attacker in order to solve our underlying problem. And so the key takeaway from this is that as long as the reduction treats the adversary, the supposed adversary that we assumed for contradiction, as long as the reduction treats the adversary as a non-interactive black box, so it just gets an input, produces an output, it's not sending messages back and forth, we only run it a single time and treat it as a black box, probably the reduction works in the quantum setting. I don't know that there's necessarily a complete rigorous theorem, but at least as intuition, this should probably hold. And so this captures things like the hybrid argument that we just saw, and as well as many of the well-known results throughout crypto. Now, throughout the talk, I'm going to keep updating this key takeaway and adding more nuance to this, because it turns out that there are some times where things break down, and so for this takeaway, we really crucially will rely on the fact that the box is non-interactive in a single run. All right. So let's move on to the second example, which is encryption. So here's, I won't formally define like what an encryption scheme is, but I'll just define what it means for an encryption scheme to be secure. And the way we define security is by the following game, and I'll elaborate on sort of the why security is defined this way in a moment, but let me just go over the game. So we imagine for encryption that the adversary that's trying to break the encryption scheme is playing a game with a challenger. The first thing the adversary does is submits two messages, M0, M1. And then the challenger chooses a random key K for the encryption scheme, chooses a random bit B, and then encrypts using the key K the message selected by the bit B, and sends the resulting ciphertext C back to the adversary. Our adversary then tries to basically just tries to tell which of the two messages was encrypted. So they send a guess B prime back for B, and we say that they win if B equals B prime. And the definition that we have is that enc is one-time secure, so it's secure for a single encrypting one time only. If for all polynomial time adversaries, the adversary can't do better than random guessing. They can always flip a random bit for B prime and win with probability a half. And the scheme is secure if an efficient adversary can't do much better. All right, we say it's one time because we're only ever seeing a single ciphertext. You need to update this definition if you wanted to see multiple ciphertexts. And now let me go over why we define security in this way, because it'll actually be important in a couple slides. So for anyone who hasn't seen crypto definitions like this before, the question is, why does the adversary get to choose the message? After all, the adversary is trying to break the scheme and learn what the message is. Why are we allowing the adversary to choose the message? And the reason is that we want the scheme to be secure for any source of messages. Maybe it's English text, maybe it's video files, etc. We could have imagined a definition with sort of a separate entity for sampling the messages. but it's sort of cleaner to just sort of group that entity together with the adversary. And there actually is precedent for the adversary actually having influence on the messages. As one example, during World War II, British intelligence would actually ask the military to lay mines in order to lay mines in a particular location, and then they would have some guess that when the enemy was communicating, that they might have been talking about the location where the mines were laid. So there's actually precedent for allowing the adversary influence on the message, and plus it's mathematically cleaner to sort of consider the everything as one entity. There's also the part that the adversary, maybe has some side information about the messages. Maybe, the adversary knows the recipient or some contents. And the adversary's goal might not be to learn the entire message, but just to learn, one piece, like when is the attack going to happen, or something like that. And the point is that basically what this definition does is it collapses all these different considerations down into a single polynomial time adversary who knows everything about the message except for one bit, namely whether it's M0 or M1, and all the adversary is trying to do is learn that single bit. So that's classical encryption. Now, what happens when we move to the quantum setting? Well, there's a straightforward generalization of classical encryption, which I'll just call post-quantum security, where we did the same thing as we did in the pseudorandom generator case, where we just replaced the polynomial time, the classical polynomial time adversary with a quantum polynomial time adversary. So this is sort of the most natural thing to do. But there's another way that you could define security, which I will call fully quantum security, where not only are we allowing the adversary to be quantum, but we're actually allowing the adversary's messages with the challenger to be quantum. So, right, if the adversary is, we're allowing the adversary to choose the message. Well, now that he's a quantum adversary, maybe it makes sense to allow the adversary to choose quantum messages. And there's some subtleties in actually getting a sensible definition that I'll only touch on. So all of this here is informal. That's why I have these asterisks here. There's some design choices in coming up with what actually makes the sensible definition. But at least to a first order approximation, why couldn't we have allowed the adversary to send a superposition of pairs of messages instead of just two classical messages, and then the adversary gets the encryption of one half of the superposition back, and their goal is to tell which one. So I'll call this full quantum security. So now the question is, which definition do we actually want? Which one makes sense? And I don't think there's a universal right answer here. But instead, which definition you use will probably depend on your use case and what kind of attacks you are thinking might be possible. So for example, if your honest users, the actual communicating parties, are classical, and they are only interacting over a classical network, and your adversary is just remote, somewhere else on this classical network, running a quantum device locally. Well, in this case, it seems rather weird to imagine the adversary influencing the honest parties enough that the honest parties encrypt a quantum message, right? Because they're classical, they're only communicating classically. How on earth is the adversary going to somehow cause them to encrypt a quantum message when they don't even have quantum capabilities? So in this case, post-quantum security is likely efficient. On the other hand, if your honest users are quantum, maybe because you're using this encryption scheme in sort of a higher level quantum protocol, or maybe you're actually allowing A to have physical access, to the honest users. Maybe the encryption is happening on a smart card and the adversary actually gets physical access to it. Now maybe you need full quantum security, because maybe now it could be realistic. Potentially, you know, we don't have quantum computers yet. We don't know what kind of attacks will be there, but it could be plausible in some of these cases that an attacker could actually cause the honest users to encrypt superpositions. Right. So, okay, so which definition you use will probably depend on your use case, and there's no universal right answer. So now the question is, you know, we have these classical proof techniques for proving the security of various crypto objects. Which version do they give us? Do they give us post-quantum security or full quantum security? So here's a standard way to build an encryption scheme. As an example, this is something called a stream cipher. So we have a secret key K, and the way we encrypt our message is we first run the key K through a pseudorandom generator to just get a long pseudorandom string, and then we XOR it with the message. And classically, we have a theorem that this works. So our theorem is that if G is a secure pseudorandom generator, then the encryption scheme is one-time secure according to our definition. And the proof is another simple hybrid argument. We assume the encryption scheme is insecure, which means that there is an efficient attacker with a noticeable advantage. And we define two hybrids. So hybrid 0 corresponds to the sort of real experiment for encryption, where the adversary actually gets an encryption of MB. We know just by the fact that our assumed adversary A is an attacker for the encryption scheme, that the probability their output B prime matches B is 1/2 plus epsilon. This is just by definition of what it means to be an attacker. On the other hand, we can consider a different experiment where the way we encrypt is, rather than using K and expanding it into a long pseudorandom string G of K, we just replace that long pseudorandom string with a truly random string and XOR that with MB. In hybrid 1, though, note that random string XOR MB is just a random string, uniformly random and independent of the choice of B. So as a consequence, no matter what the adversary does in hybrid 1, the probability B equals B prime is exactly 1/2. And so what we can do is we can easily take the fact that these two hybrids have an epsilon difference between the probabilities that B prime is equal to B, and we can use that to construct an adversary capital B with advantage epsilon that actually breaks the underlying PRG. So when we move to the quantum setting, we'll start with a post-quantum PRG. So we'll assume our PRG is secure against post-quantum attackers. And well, actually, if the definition of security uses post-quantum security, so quantum attacker but classical interaction, everything works. Again, it's, you know, you just basically update L instances of probabilistic polynomial time to quantum polynomial time. And the reason is basically the same as what we had before with the pseudorandom generator case, that the proof doesn't care how A works internally as long as it has a non-negligible advantage. And so we also get, you know, our classical reduction sort of trivially lives to give us a post-quantum reduction. On the other hand, this scheme does not actually give us a full quantum encryption scheme. We can actually prove this. And here's like one concrete attack that you could do. So remember, in the full quantum case, our attacker is allowed to create superpositions over pairs of messages. So we create a superposition over M, 0. So uniform superposition, all messages get the same weight in the sort of the first message register, and the second register is all zeros. So if we're in the case where the challenger flips a bit b equals 0. In this case, we encrypt the left register. So what gets XORed with M is G of K. And since we're in the uniform superposition, this G of K XOR M just basically permutes all of the values of M. And actually what ends up happening is we're still in a uniform superposition over all messages. On the other hand, if B equals 1, what gets encrypted is 0. Just this basically single classical message 0. And so what the adversary sees in response is G of K for a random key K. And we can easily distinguish these. A uniform superposition, if we were to apply the Hadamard transformation, will just give us the L0 string, where sort of this quantity, even though it's a random string, when you apply the Hadamard, you actually also get essentially also a random string. So you just by applying Hadamard and measuring, here you'll get 0, and here you'll get a random string, and so you can easily distinguish these two cases. So the question is then, like, what went wrong? Like, why doesn't the classical security proof lift to the full quantum setting? And the reason is that the adversary is no longer a black box of classical interaction. Yeah, we might still try to treat the adversary as a black box, but our new adversary for the full quantum security, the encryption scheme, is exchanging quantum messages, right? It sends a superposition over pairs of messages and gets a superposition of encrypted messages in return. And so we've changed not only the computational model of the adversary, which, to a first order approximation doesn't enter into the crypto proofs, but we've also changed the model of interaction. And the classical security proof, actually crucially, it turned sort of implicit in the fact that our encryption scheme is not fully quantum secure. It turns out that the classical security proof crucially relied on the fact that the classical adversary was only making classical interaction. Once we allow the quantum interaction, things break. And so so here I'm going to update the takeaway from before to say that as long as the reduction treats the adversary as a single run black box, but potentially with classical interaction, the reduction likely works in the quantum setting. So now we're allowing our black box, that is the adversary, to interact and send messages back and forth, but the messages have to be classical. Once you allow quantum messages, all bets are off. Okay, so I'll just briefly mention that we, nevertheless, even though our particular scheme was insecure against quantum attacks, you can still consider other schemes. So the question is, can we construct a fully quantum secure encryption scheme? And it sort of depends on the definition. Some definitions are unattainable. There's attacks no matter what you do. But then there are other ways to actually sort of formalize everything where you actually get an attainable definition that makes sense for encrypting quantum messages. And here's just one example of how you might do this. Basically, what you do is you apply a pairwise independent function to your message. And I won't prove this. Basically, the way you prove it is you can sort of look at the density matrix or something like that of what the ciphertext looks like, and see that it hides all contents of the message. But maybe at a more intuitive level, the scheme from before, XORed with the message, you can think of that as sort of one-wise independence. And as is often the case when going from classical to quantum, ones turn into twos. So instead of a one-wise independent function, you do a two-wise independent function. So I'll leave it at that. Maybe I'll pause to see if there are any questions.
Well, I was asking a question about why not multiple runs with classical interaction? Like why doesn't why shouldn't classical security proofs lift the quantum ones in that case? But Andrea says the issue is probably rewinding.
Yeah, and that's going to be the next example.
Thanks. Got
Yep.
it.
Yes. So with that, let's start the next example. So here we're going to look at the case of something called a commitment. So commitment is sort of the digital analog of a locked box. So to run the commitment algorithm, you have a message, you choose some random coins, and you feed them into the commitment scheme, and out comes another string called the commitment. There's a hiding property that we won't discuss, which asks that the commitment hides the message. But the more important thing for our purposes is going to be binding, which says that if I give you the locked box, if I give you C, the commitment, that I can't later pretend that I committed to something else. So we say that COM is computationally binding if it's infeasible for here we'll start in the classical setting, if it's infeasible for an efficient classical adversary to find a collision, to find two messages and randomnesses that map to the same commitment. If you could do this, then you can you can cheat basically, and send your one commitment and then later pretend that you committed to to either of two different messages. But by insisting on computational binding, you can't do this, is the hope. That there's no way to open the commitment to two different things. So the question is, what do commitments look like in the quantum setting? And the natural thing you might try to do is just do the same thing we did before, and you replace all instances of classical with quantum. So you just replace your classical polynomial time adversary with a quantum polynomial time adversary, but the adversary's goal is the same, to produce two messages and randomnesses that map to the same commitment. It turns out that this actually won't work though, or it's not sufficient. And to motivate this, consider the following coin tossing application of commitments. So Alice and Bob want to establish a random bit between the two of them, but they don't trust each other. So what they're going to do is Alice is going to choose a random bit and commit to it. So she's going to choose a random BA and some random coins R and send the commitment of BA using the randomness R. The hiding property, which we didn't discuss, means that the bit BA is hidden. So Bob doesn't know anything about BA. Now he chooses this random bit BB and sends it to Alice. Because he doesn't know anything about BA, his BB should be, independent of BA. And what we're going to do is define the output bit as the XOR of BA and BB. So what Alice does is then she sends BA back to Bob, as well as sort of the proof that she actually committed to BA. So she sends it, or proof or an opening. So she sends the random coins R. And this allows Bob to verify that Alice didn't sort of cheat and change her BA after seeing BB. Right, and so the intuition is that Bob can't bias the output because he doesn't know what BA is when he has to choose BB. And Alice can't bias the output because she committed to her BA before seeing BB. Okay, and in the classical setting, we can actually formalize this intuition and prove that Alice can't bias the bit B. So let's suppose that Alice wants to force the bit to be 0. And suppose that she can cause the output bit to be 0 with probability noticeably larger than a half. Well, what this means, for her, half of the time Bob's bit is 0 and half the time Bob's bit is 1. We know that because Alice sort of succeeds more than half the time, she must have a good chance of opening to Bob's bit in both the case where the bit is 0 and 1. So if she can match BA to BB, then she causes the output bit to be 0. And by her ability to bias, her assumed ability to bias, we know that she can basically match Bob's bit with non-trivial probability in both cases. So now what we do is we derive a contradiction. We're going to extract from this adversary a collision for the commitment scheme. So we first, the way we're going to do that is we're going to first run the adversary A, playing the role of Bob, but with bit 0. And so the adversary outputs something. Now what we're going to do is we're going to actually rewind the adversary to just after the adversary committed to C, but before anything else. So we're going to sort of go back in time to just after the adversary sent the commitment to her bit. And now we're going to finish the run again, but this time using having Bob set his bit to be 1, and we'll get the response of the adversary. And the key point is that sort of once you've conditioned on the commitment here, both runs in step 1 and step 3 are actually independent, because they start from the same state of the adversary. And we know that both runs have a non-trivial chance of sort of having Alice successfully match Bob's bit. And what we see immediately is that what we get by looking at the final message of the adversary in both steps 1 and 3, we get exactly a collision. We get we get 2 openings to the commitment C, but with different bits. And because they're independent, the probabilities just multiply, and we get a non-negligible chance of succeeding. But what happens in the quantum setting? Well, in the quantum setting, we can do step 1, that's fine. But now when we try to do step 2, we're in trouble. And the reason is that A is now a quantum attacker, and they're keeping a quantum state as they're going. So they have some quantum memory and some quantum state in that memory as they're going. And every time we extract something from the adversary, and in particular, when we extract the final message from the adversary, this is a classical string. And so in order to extract this classical string from the adversary's quantum state, a measurement had to happen. But this measurement means that the adversary state is irreversibly altered. And so we can't, at least in a computationally efficient manner, we can't return to the adversary state at a prior point in time. It's been destroyed. And so we're in trouble. And this can be formalized. And so there's this theorem by Banis, Rosmanis, and Unruh that basically shows, relative to a quantum oracle, that there's a commitment that is post-quantum binding, meaning you can't find a collision, but for which Alice can nevertheless break the coin tossing game. So it's not just an issue with the proof technique. There really is a barrier here. So because of this, we need to, when we're trying to expand our key takeaway, we need to be careful. So here I'll give sort of the final version of it, which is, as long as the reduction treats A as a single run black box, potentially allowing for classical interaction, the reduction likely works in the quantum setting. But again, if interaction is quantum, all bets are off. And now also, if we ever have to rewind the adversary, all bets are off. And this is true, here we're never considering quantum interaction. We're only focusing on classical interaction, and yet there's a problem. So it really is crucial that we treat A as a single run for this. So I'm sort of running out of time, but I'll just briefly mention that there is a solution to this, and the idea basically is to enhance the commitment scheme. Maybe I'll just skip through this. So one thing is that it turns out that if your scheme is perfectly binding, then actually everything works. And the reason is that the opening that Alice sends is actually uniquely determined by the commitment. And so what that means is that we didn't actually have to do any measurements to extract the opening from Alice. By the fact that the opening was a valid opening of the commitment, it's already been uniquely determined. It basically already has been measured and collapsed, sort of implicitly. so we can actually then run through the proof, obtain a collision, which thereby contradicts perfect binding. Now, perfect binding isn't always good. So perfect binding means there doesn't exist any collisions, and therefore your commitment actually has to be larger than the message. For this bit flipping example, that's not a big deal, but in other settings, it's a problem. So a better definition is something called collapsing, which more or less just directly captures what we need, which is the ability to measure Alice's opening without her detecting that we measured the opening. And if you can do that, if their commitment scheme has the property that you can measure the opening without detection, then you can get the proof to go through. And as a result of this, collapse binding has become sort of the standard goal for post-quantum commitments. And then, okay, so we know that we can achieve this coin tossing with a collapse binding commitment, and then the last bit is just how do we build these things, and it takes some effort. There's a theorem by Unruh that random oracles, so a truly random function, is collapse binding. And then in some other work, it was shown that you can construct collapse binding commitments from lattices. But the point is that these proofs have to be sort of inherently quantum proofs now, because our definition for the quantum security of a commitment scheme is now actually a quantum definition. Like we're actually, the goal of the adversary is a quantum, they're actually sending quantum information. They're sending, they're getting a quantum opening and asking whether it's measured or not. So these arguments have to be inherently quantum. And so a key takeaway from this is that even if you're only worried about attacks over classical channels, sometimes you need to consider security under some quantum interaction notion, like a collapse binding commitment. Okay, so in the last couple minutes, I'll just talk about the fourth example, which is something called the random oracle model. The random oracle model is motivated as follows. So many crypto systems out there make use of a cryptographic hash function. But it turns out that we don't know how to prove many of these secure just under the assumption that the hash function is, I don't know, collision resistant or one way or something like that. And so a common practice now is to pretend that the hash function is actually, so well designed that it basically acts like a random function, or a random oracle. So the crypto systems, they just evaluate the hash on various inputs, so they can sort of, they already treat the hash function like a random oracle, and the assumption is essentially that the adversary also treats the hash function like a random oracle, that they don't gain any advantage by looking at the program code. So when we move to the quantum setting, the question is what happens in the random oracle model. And the point, I guess, is that in the real world, there isn't a random oracle. Random oracles don't exist in the real world. In the real world, it's a concrete hash function. And the adversary can certainly query this concrete hash function on superpositions of inputs to run Grover's algorithm or the BHT algorithm for finding collisions. And so the only way to sensibly capture the adversaries that may try to run Grover's algorithm or whatnot is to allow our adversary when we're sort of in this switching to the pretend world where our hash function is replaced by a random oracle, we allow the adversary to make quantum queries to the random oracle. It's the only way that we can sensibly capture attacks of this form. And so this has now become sort of the standard goal in the random oracle model for post-quantum crypto, is to justify security when you make quantum interaction to the random oracle. But it turns out that the classical proofs don't carry over to the quantum random oracle, even if the goal was sort of a definition with classical interaction. So even if your encryption scheme, even if you're only targeting post-quantum security, there's no rewinding. no quantum interaction or anything like that, it turns out that the proof still doesn't carry over to the quantum setting, because our modeling of the adversary, yeah, sure, it's interacting with the challenger, making classical queries, but the adversary is now making quantum queries to the random oracle. So even if the experiment is a classical experiment, we're modeling our adversary as a adversary with quantum interaction. And based on everything we've just talked about, once you have once your adversary is allowed quantum interaction, the classical security proofs generally don't work. And the bad news is there are actually some negative results. I won't say what this means, but there are cases where the contrived cases where the quantum random oracle fails. But the good news is that most major results have been reproved. Okay, I guess I have one more thing before we end, which is that there is actually a silver lining to all of this. And this was some work by myself and some co-authors, where we actually observed that these bad cases, these sort of bad cases where the classical proofs don't lift to the quantum setting, actually can be turned around and turned into useful things. And in particular, the setting of a post-quantum commitment scheme where the coin tossing game is insecure actually leads to novel applications such as quantum money and other things like this. And the intuition is that if you can win the coin tossing game, and yet the commitment scheme is post-quantum secure, essentially that implies that the adversary has a quantum state and it's unclonable. If it were clonable, then you could sort of skip the rewinding step and use the two clones in the two executions in steps 1 and 3. So the fact that the adversary can win while the commitment scheme is post-quantum secure means that the adversary state is quantum and unclonable, and you can actually leverage this. You can take a supposed adversary and actually use that adversary to build a new crypto system, where they basically prove to some other party that they have a quantum and unclonable state, and this gives you novel applications like quantum money and so forth. So there is a silver lining to all this that I just wanted to mention. And now I am done, and the summary for my talk is that post-quantum crypto is more than just lattices. Really there's a sort of a rich landscape of things that need to be solved, from underlying computational assumptions, understanding the right security definitions, to actually updating our classical proofs to give proofs that make sense in the quantum setting. And so with that, I will finish my talk.
Thanks a lot, Mark. Thanks for this the great talk. Let's see. We are now going to start our panel. So, Mark, if you could stop sharing your screen.
Yep.
Oh, great. So, so we have a sorry. Before we start with the